Alright, so in this video what I'm gonna try to do is explain a concept that we use very often in programming, but using a spreadsheet. Now it's called refactoring. And now it's difficult to explain what refactoring is using code because not many people understand code. But there's many people that understand spreadsheets. So hopefully you will see what this concept is and how it might help you actually if you're not a programmer, how to improve or clean up spreadsheets. There's advantages and disadvantages, but yeah, hopefully you will see the point. So let's see this example. Um, in this spreadsheet, uh, I have um, inflation essentially. This is the consumer price index of Mexico by year. This is the official data, and there's a problem with this which I'm gonna tackle later. But first, uh, my objective is to get the inflation by chunks of 6 years. Now, why 6 years? Because in Mexico, presidents have a 6-year terms. So I want to see the inflation by president, essentially. And so to get the inflation per year is relatively simple. Just the index of 1 year divided by the index of the previous year minus 1. So that's the percentage, the inflation in terms of percentage yearly. Now to do the same for a period of 6 years is essentially the same, except instead of previous year is 6 years before. Okay, now, so the first problem is that 28% doesn't tell much because people are not used to look at 6-year inflation. So there's a way to convert this into something that is like a year, which is annualizing. So the formula is essentially exponential 1/6 of the original difference. So in this case it's 4.27%. Now that's much more understandable to people. So you can think that every year the inflation increased by 4.27% for 6 years. Now, if we do the calculation, for example, starting from here, with that index 1 plus this inflation, at the end of 6 years, we get exactly the same output, 80. But if you look at the numbers and the indexes by year, it's not exactly the same. And the reason why is if I copy this formula for the yearly inflation, in the original data, the inflation changes, is variable. And in this, the inflation is constant. But it doesn't matter, the end result is the same. So this is a way of simplifying 6 years into a single number. And you may think like, why not use the average? Well, if you use the average, the number that you get is not the same. In this case it looks the same, but it's not. Yeah, it's close, but it's not the same. Now, if the inflation is bigger and the rate of change is bigger, this number is much more different. But so we'll see that later. But essentially, you cannot use the average. Uh, it has to be done something like this. So the problem is that the official data is only up to 2003. That's it. And I'm interested in more years. Now, so this is a problem. I found historic inflation in somewhere else. This is not official. I don't know where they got this from, but uh, they match with the official numbers. But this is percentage per year. So I cannot do the same operation here. So that's the problem. Um, like how do I get this number but from this data? Now, uh, one way is to start with some fake index. I start with 100, that's the base, and then I calculate the rest of the indexes based on the yearly inflation. So this number is very different from the official uh, consumer price index, but it achieves exactly the same purpose because I can divide one by the other by year, and the result is exactly the same rate of inflation. Right. So this is correct. This is useful, even though it's kind of fake. But it doesn't matter because it allows me to do the same operation. I can take this year divided by 6 years before, and then analyze it. Parentheses here. That's it. And I can do the same for every period. Okay, so this is what I want. And if you see, for example, this one, average, this is way different than this one because bigger inflation and like 160% 1 year. So average doesn't work for what I want. Now these are not very nice because these are spread out. I want them one after the other. Okay, so this and then this and so on. So these are separated by 6 rows. So for example, it starts with D2 and then the other one is D8. And then it's going to be D14 and so on. So there is a way to get that the value of that cell programmatically, and that's with the offset function. In offset, you specify a reference, let's say D8, and lock it. And then if I say 0, 0, it's just gonna return the same cell. But if I do 1, it's gonna be the one below, and then 2, 2 rows below, and so on. So I want first is gonna be 0, and the next one is gonna be 6. Right? That's D14. So it's going to be like 0, 6, and so on. So let's use that instead. Like that. But so this is correct, right? 849. Yeah. But I don't want this number. I want to calculate it using a year. So this is going to be 1971, and then it's going to be that plus 6, and then so on. Let's remove this. No, not yet. Okay, now I'm going to copy the percents. All except the last one, because the term has not ended and the formula is different. Okay, so I want to calculate this number based on this year. So it's like this minus that. That is correct. So instead of J, I'm going to use that. So that's the same thing, and now I can delete this. Okay. So this is the offset using a formula based on this year. I get the right range, well, the right cell or reference to the cell. So it's going to be D8, and the formula is D8 divided by D2 and then analyzed. So it's D8 divided by D2. Okay, and then this analyzed minus 1. There it is. So this is 83.44, 15.164, 21.77. So that is correct. Now I don't need this. I don't need this. This is the result that I'm looking for. The inflation for a period of 6 years, but analyzed. So it's meaningful. And that's it. This is problem solved. Now just to check, if I start with 100 and then I multiply that by 1 plus that yearly inflation, but exponent to the 6th, because it's 6 years of that inflation, the result is 229, which is what I get at the end of the 6-year period. And if I do that over and over, the last one is, for example, 812, 811, 812, 811. So yeah, this works. So this is where most people will say like, okay, job done, let's go home. But not programmers. Because, I mean, what is this? This is just garbage. It's useful only to get this number, but this number by itself is not meaningful. It doesn't tell me anything. So yeah, I can just hide that column, but yeah, that's not what programmers do. So this is where refactoring starts. I want this number without using this column. I think there must be a way, and there's always a way, But what is this most straightforward way to show that? Okay, so first, this number is arbitrary. It could be 1, it could be 2, it could be whatever. It doesn't matter because all that matters is the rate of change. So if I start with 1, this function, first let's simplify this function. Because this offset is just adding noise because it's D8. And then this offset is more noise because it's just D2, right? D8 divided by D2, and then analyzed. Okay, but D2 is 1. So this is nothing more than D8. That's it. So this is the inflation of 6 years, essentially. So how can I get this number without this column? Basically, that's the problem. Now, let's give it a try. So I'm gonna copy this here, and I'm gonna try to replicate the same. So D8, what is D8? D8 is D7 times 1 plus B8. Okay, so just replace that. The result is the same, obviously. And then replace D7 with that, the contents of D7. And so on. What's D6 now? It's this. So this is just substituting one after the other. But the pattern is becoming clear. It's 8, 7, 6. Well, the next one has to be 5. And the next one has to be 4. And the next one has to be 3. And yep, so this is the same as this, except now the function is not using any data from the D column. I can just delete it and it still works, right? So this is what I want. This is doing exactly the same as this, but in multiple steps. And for the next row, I have to start with B9. So it's cumbersome because now I have to manually do 11, 12, 13, 14. But yeah, the result is correct. Now I have to find a way to do this without manually using every typing every one of these. But the pattern is obvious. Each one of these is plus 1. So I can do that here in this column, for example. 1 plus that. That's it. And then I have to multiply each one of these values. And there is a function for that. Product this and analyzed -1. That's it. This is exactly the same thing. But there's a problem because now we need this column. So we traded this garbage column by this garbage column. So essentially we gain nothing. But here's a trick that many people don't know, and this is array functions, and this is a whole subject that there should be a whole video for that, but I'm gonna try to explain it simply, just to show how it helps us in this example. So normally people work with one cell, one value, 1, 2, 3. So they have the data, and then they have a function that uses that data. So in this case, it's 4 cells, 3 data, 1 function. Now, with array functions, you can have a single cell that contains 3 values, or any number of values. And then, on the same cell, have the function. So this is kind of hiding 3 values of data in a single cell. So instead of 4 cells, only one cell. So that's essentially array functions, or the core of array functions. Now, how do we use this for our example? I can specify a range, but it tells me there's an error. To get the values for the entire range, use the array formula function. And to use the array formula, there's a shortcut, Ctrl+Shift+Enter, which adds this syntax, array formula. It's different in Excel, it's different in other software, but the shortcut is the same, Ctrl+Shift+Enter. Now, if you do that, now you get an array of values, in this case 6 rows. And the advantage is that now I can do, like here I was doing 1 plus B3, but now I can do 1 plus, and instead of B3, an entire range. So this formula is going to be applied not for a single cell, but for an array of values. And there it is. Let me move them here. These values come from a single formula in a single cell, while these values are 6 formulas in 6 cells. So that's the difference. But now I can do the operation here. I can just say product of that. So that is hidden. The values are hidden. I don't need to show them. And if I don't need to show them, then I don't show them. So that's it. The result is exactly the same, except now I don't need this column, right? I can just use this. So this is the same as this. And then the next one will have to be from B9 to B14. There it is. So these two are equivalent. It's just another way to do the same thing. And the result is exactly the same. So now all I need is to find a way to get these ranges parametrically, because I don't want to manually specify the next range. So to do that, I can use the same trick I use here with this function offset. Okay, so here we have an offset from D8 based on the year. So that will be D8 because initially it's 0. But instead of D8, I want B3. So that's it, 4.96%. So that's correct. But the good thing about the offset is that there's these two parameters, height and width. So in this case, I want 6 rows and 1 column. And there it is. This function returns an array of values. And then I don't want those values actually. I want 1 plus those values. So I can do that with array formulas. So if I do 1 plus that range, it will not work. But if I do Ctrl Shift Enter, which adds array formula, I get exactly what I want, which is 1 plus all of those values. And then of course I can do the same thing. I can do product that analyzed -1, and there it is. That's the result I want, and I can do the same for all of the rest, and the values are exactly the same as the original ones. Can I compare them? 0, 0, 0, 0, 0. They are exactly the same. So this is refactoring. The way in which I got to this result is completely different, but the result is exactly the same. Now I can remove all of these. I will move this to here. And now I don't need this column. I can just get rid of it. And that's it. The code has been refactored. So this is what is called functionally identical. The function is completely different, but the behavior of the function is exactly the same. This is refactoring. Now, a lot of people will say like, but why? What's the advantage? I mean, first of all, is cleaner because now there's nothing else. It's just the raw data. There's some years here, and then a single formula per year, and that's it. And it's not just cleaner, but it's more maintainable. If you want to do any change, you can just change it in one single place, and you can do, for example, let's say instead of 6 years, let's do 12 years, right? That's the inflation of 12 years. Or let's say that you don't want it annualized. Well, then just don't show it annualized, and that's it. So it's much easier to make changes. And that's why programmers refactor code, to make it easier to make changes in the future. Yeah, it's more work now, but at the end it usually pays off. So yeah, that's it. That's an example of refactoring, and maybe you will find it useful for your spreadsheets, but if not, I mean, this is a trade-off. It's you're exchanging complexity, because before there were a lot of formulas in many cells. Each one of those formulas was simple, was not complicated, but the whole thing was difficult to understand. Now you change that for simplicity. because it's only one function that is more complicated. So it's not the same thing, complex and complicated, but anyway, it's a trade-off. Sometimes you will want that, sometimes maybe not. It depends. But yeah, maybe you will find it useful, and if not, uh, well, this is what programmers do all the time. Try to take something that is complex and make it simple. If you understand the code, which if you're a programmer, it behooves you to do that. So that's it. I'm gonna clean this up and add the link to the video, so you can take a look at it. Well, that's it. Hopefully you find this information useful, and maybe you learned a few tricks. Uh, Bye.